Now we're going to talk about three types of molecules: carboxylic acids, esters, and amides. So carboxylic acids are indicated by what's called a carboxyl group. And so a carboxyl group, we would recognize it's a carbonyl where the carbon atom is bonded to a hydroxyl group. So if we look at this molecule, acetic acid, right here, if we look at the three-dimensional representation, we have the carbonyl, that's a carbon atom double bonded to oxygen, and we have a hydroxyl, oxygen bonded to a hydrogen. And so that looks like kind of patterns that we've seen before, but because they are next to each other, they're not two separate groups. Instead, we call that whole thing a carboxyl group because they all of those atoms, when they're linked together, behave in a unique way that's different from when it's just a carbonyl or just a hydroxyl. So this whole thing is called a carboxyl group. Any molecule with a carboxyl group is then called a carboxylic acid. When we're looking at carboxylic acids in molecular formulas, COOH is the most common representation that we see. We've seen this previously when we were talking about acids. We know that COOH in a formula indicates that a molecule is an acid, and specifically it's a carboxylic acid. The most important property of carboxylic acids, true to their name, they are acids. So that hydrogen atom that's in the carboxyl group is the hydrogen atom that is acidic. That's the one that can be donated. So what ends up happening is basically this H right here can be donated as a proton, leaving the negative charge on the oxygen atom right there that's in the carboxyl group. And then what ends up happening, the reason why this is relatively stable is that, again, the fact that it's next to that carbonyl means you have the ability to basically spread the charge around across that other oxygen atom. So you have this kind of sharing where you have this resonance stabilizing the anion that's formed. And so in the world of organic chemistry, carboxylic acids are the acids. So if you're doing something, if there's some sort of chemistry you're trying to run with organic compounds, a carboxylic acid, if you need an acid, you got to use a carboxylic acid. And similarly, biologically, acids that function biologically are carboxylic acids. And even if you think about like acetic acid, it's kind of our stereotypical carboxylic acid. It is the active ingredient in vinegar, right? And if you think of like in cooking, in the world of cooking, you use acids all the time. And vinegar is a very, very common acid that you use in cooking because it's an organic acid. You don't use like sulfuric acid very much in cooking. You use acetic acid. It's the organic acid, or it's an organic acid. It's one of the easiest ones to get and safest. And so that's why you see it so much in like cooking, because you're in like an organic kind of mind space or an organic chemistry when you're dealing with food. So a related compound is called an ester. And just like with carboxylic acids, an ester functionality is defined by a carbonyl next to an ether oxygen. So again, it's this idea where you have two groups that we would have seen previously, and when they're next to each other, there's like a synergy where they work together. This whole thing is called an ester group. And actually, it's an ester molecule. This is an ester group. We don't have any sort of fancy name for the group. It all has the same name. And in a molecular formula and condensed structure, we write COO. So that's we really want to be careful there. COO. A lot of times when we kind of see that, we would think it's just like a bunch of things bonded together, right? Like, you know, single bond O, something like that. But we do really want to be careful. That is going to be an ester where it goes up. The ending for names is O8. So O8, if you see that on the back of a formula, that is a sign that it is an ester that you are dealing with. One of the most common ways that you interact with esters is through the taste of fruits. So when you think of like fruity flavors or like something that tastes like a fruit, oftentimes that flavor or that kind of essence is represented or captured by an ester molecule. So there's all sorts of different esters that are shown up on the screen with the associated fruits. So isoamyl acetate is the flavor of pears. Octyl acetate is the flavor of oranges. I think that's a plum for isoamyl butyrate. We got raspberries and pineapples on there as well. And so the thing is, it's not to say that like in an orange, the only molecules are octyl acetates. Instead, octyl acetate tastes as kind of the purest essence of orange. So this more of in an actual orange, there's going to be a lot of esters and a lot of other molecules that are all related to each other that kind of convey that sort of orangey flavor. But if you get like orange candy, it's probably a lot of octyl acetate that is conveying the sort of orange flavor that you're dealing with, or something like that, right? That sort of pure sense, and it's only the one molecule that's conveying that flavor. But still, if you were to eat formic acid isobutyl ester, it's probably going to taste quite a bit like raspberry. Amides are then another similar related type of molecule where we see a carbonyl next to what we would call an amine, right? This is a carbon atom in a carbonyl that is single bonded to a nitrogen atom. So previously we said nitrogen atoms with all single bonds, we call those amines. When it's next to a carbonyl though, it's an amide. And again, just like esters, this is just called an amide group, and the molecule is also called an amide. When you're naming, you just put amide in the name. As these things get more and more complicated, you just kind of throw the name in there. Very kind of clearly are stating this is called, acetamide. It's just an amide. The nitrogen atom in the amide can be bonded to other carbon atoms or hydrogen atoms. This is one of the unique things about amides versus esters and carboxylic acids, in that you can have kind of this end of the molecule, like we have up here, where the nitrogen's just kind of hanging off. There's hydrogens attached, or you can see there can be kind of these carbon atoms where you can have some structure on the other side of the amide. And maybe the carbonyl can be the end of the atom because, say, that's a hydrogen over there, but that still would be called an amide because it's a carbonyl where the carbon atom is single bonded to a nitrogen. So the reason why esters, amides, and carboxylic acids are all here together is that these molecules are inherently linked together. Namely, that you can react a carboxylic acid with alcohols and amines to make esters and amides respectively. So I have two reactions that I've drawn up here, and it's a carboxylic acid reacting with either an alcohol or an amine to make ester or amide. And so in both cases, it's a very similar reaction pattern where the OH group from the carboxylic acid basically gets swapped out with a larger group to attach into that carbonyl group right there. So we can see in the case of the carboxylic acid and the alcohol, basically the entire rest of the alcohol gets attached into the carbonyl to form that ester molecule. And then basically what was the OH from the carboxylic acid becomes a water molecule, right? So you get kind of this replacement where the carbonyl is kind of a group where you can kind of change what the decoration of the carbonyl is. Is it just an OH where it's a carboxylic acid? Is it an alcohol part that's hanging off? Then it's an ester. Do you react it with an amine where you can again replace that OH and turn it into water? So we're seeing again these ideas that carboxylic acids, one of their functional groups that they react as acids. The other aspect of the functional group of a carboxyl group is that OH can leave, that OH can be replaced and something more complicated put into its place. So you can make an ester or an amide out of a carboxylic acid. And these can also be replaced. These have different relative stabilities, but again, that kind of the ester, you can react an ester and turn it into an amide. You can turn an amide into a carboxylic acid into an ester. You can swap these things out based on what other molecules you put present, how you're pushing your equilibrium. So this idea of forming esters from carboxylic acids and alcohols has a very important application. If you take a molecule like, say, this over here that has carboxylic acids on two sides, so carboxyl group, and then a molecule with a hydroxyl group and a hydroxyl group, right, on both sides, and you let these react with each other. And we can see that what would happen is you can end up forming chains because one side of the molecule can react with, say, one side of the double carboxylic acid can react with an alcohol, and another one can react with another alcohol, and these can keep linking together across these different groups, and you can make a long chain that is held together by these ester bonds. This is a bit more controlled chemistry than what we were looking at before with taking carbon-carbon double bonds, the alkenes, and forming these polymer chains. But you can do it in a much more kind of controlled and chemical way where, it's kind of these links that the acid reacts with the alcohol, and kind of you form this kind of directionality where you put these sort of linkages together. And you make these long chain molecules that are, again, a type of polymer. These long chains of polymer molecules can be folded into fibers that are called polyester fibers. So that term polyester comes from the fact that you're making a polymer out of these ester bonds. Okay, and so you can make these molecules that are long chains. You can spin those into fibers similar to the fibers you would make from, say, cotton, and that's how you make synthetic clothing. So synthetic clothing comes from polyester is a really common form of synthetic clothing where the actual strands, the actual threads that you sew together to make the clothing are made up of polyester molecules. Also, the polyester is really common plastic. Recycling symbol 1 is called polyethylene terephthalate. That is the molecule that I showed on the last slide. That is recycling number 1. It's really commonly used in soda bottles or a lot of single-use plastics. Those are all polyethylene terephthalate. It's really easy. It's a relatively easy plastic to work with. So you can make it into a lot of shapes, obviously fibers to make clothes, bottles, and you can do a lot of things like that. But again, it's these molecules that have long chains that you can then kind of make threads out of, and then you can weave those threads or press those threads into, melt them into making plastic shapes like bottles. Amides similarly react with carboxylic acids to form, you can form amides by reacting carboxylic acids with amines in the same way. The thing about this process is that when you do this process, you take a carboxylic acid and you react it with an amine to make an amide. That's a really strong bond right here. This carbon-nitrogen bond is really quite strong. It's not too hard to make. And it holds together pretty well. It's not impossible to break. It's not as strong as a carbon-carbon bond, but amides are very stable. They're quite strong molecules that you can make out of this. You can also react amides with carboxylic acids in the same way that we saw with polyesters to make long chains, what we call polyamides. Generally, we don't use the term polyester, is commonly used to talk about the fabrics. Polyamide isn't that common, but you are probably familiar with the word nylon. Nylon is the kind of trade term for fibers that are made from polyamides, where it's the same idea. You have a molecule that is a carboxylic acid on two sides. You have another molecule that's an amine on two sides, and you react them together. Right, you react them together, you make these chains, you can turn those chains into threads and put them together. Nylon is one type of polyamide. This is not it. This particular polyamide that we're looking at is called Kevlar. And so one of the important aspects of polyamides instead of polyesters is that these blue circles are nitrogen. And so they're double bonded. Here's your carbonyl, your double bond, and here's the nitrogen right here. And importantly, that nitrogen is still bonded to a hydrogen atom. What that means is that the polyamide chains can form hydrogen bonds with other polyamide chains, right? Because you got a carbonyl double bond right here, and then you have these NH bonds right here, and they can form hydrogen bonds with other threads. Okay. And so if you have these polyamide chains, that's a lot of hydrogen bonds, and they can all link up together. And so you can make Kevlar, which is bulletproof vesting material. You have these molecules that are really tightly bound together from these amide bonds. Then the different molecules link up. You can see they fit together like teeth, right, with these hydrogen bonds. A hydrogen bond isn't that strong, but these molecules are hundreds of amide groups long, linking up together. That's hundreds of hydrogen bonds. That's really strong together. And that's how you can make these really strong materials like bulletproof out of these are bulletproof vesting materials or something like that out of these organic molecules, right? The same similar type of chemistry that's using, making nylon clothing is what's going in there. Now, different designs and different types of molecules are working to do that. But this is what, and Kevlar is a brand name. A lot of these things, Kevlar, nylon, are brand names. They're not necessarily the name of a molecule, they're the name of a product. And so, but this is just an example of the particular aspects of amide. Really importantly, one of the most important things about amides is that that nitrogen atom has that hydrogen, that it can still form these hydrogen bonds. And that has a lot of even biological importance and stuff like that where there are amides in your body. Participation 5.1, question 2. Classify each of the following compounds. A, B, C, D, and E. This is the second question on participation 5.1, due Friday, May 1st at 11:59 p.m. over on Blackboard. Link to the assignment is right below the document where these videos are posted. Again, classify each of these compounds. It's A, B, C, D, and E. So those are 5 organic molecules. I would like you to tell me what type of organic molecule. How would we classify each of those organic molecules? There's some different types of representations, different ideas, kind of summing up everything we've seen in chapter 20. That's it for chapter 20. When we're talking about organic compounds, especially at this level, we're more focused on, a lot of it is on those kind of recognizing things like the functional groups, the names of the different compounds that we have, those different categories of compounds, some of their kind of broad trends, physical properties, and then representing them, right? The condensed formulas, the line angle drawings, that kind of stuff, being able to recognize what's going on. We're not really doing reactions with them here. We just want to be able to kind of recognize what's being described in a compound. Okay. There are 4 questions on participate. 2 questions. Right? There's 2 questions across 4 videos. On participation 5.1, you want to find both those questions, get those answers submitted. The only video that's left is the answers to that participation. That'll pop up on Friday night. Otherwise, that is it from me. Please do not forget the homework. It is due on Saturday. It is still part of it. This is a good practice. This material is going to be on next week's final exam. So this is like one of the only assignments you really get to do about it. I really encourage you to take a look at it. It's the most often forgotten homework. It is still part of the grade. It can help prepare you for the final exam, get some more practice with organic chemistry. If you have any questions about anything, let me know. Otherwise, I'll see you next Wednesday for the final exam or the answers to the participation that go live Friday night. Otherwise, take it easy. Enjoy your weekend. I'll see you next week. Bye-bye.